Hi, the goal of this video will be for you to learn about learning theory. Pretty cool, huh? So the core thing of learning theory is actually generalization. This is the problem we want to solve. So I'll just remind you what is generalization actually. So we're in this supervised learning setting, and we always consider this unknown target function f. This is like the central thing we consider. And what we want to do is we want to approximate f. We want to find some h that approximates f. So h will be a hypothesis, and we want it to approximate f. To do this, we have data, and our data has the following form. We have like these pairs x1, y1, and we have multiple of these. We actually have n of these pairs, and each of these pairs, well, each xi is in x, where is in our input space x, right? This is like our input space, and then we'll have the yi's will be actually f of xi, right? Which will also be in y. So these will basically have a lot of samples here where well, this guy will be f of x1, and this guy would be f of x capital N. So we'll have a lot of examples of the input to this unknown target function, and then we'll also know on these inputs what does the target function actually say. So we'll have a lot of examples where we actually know the behavior of f, and we want to use this to approximate h. So in the previous videos of the linear models, you saw that we made this notion of approximation a bit more concise by defining the in-sample error rate of h. So then we said if h has low error, then it approximates f well. So this was defined as the sum of is1 to n. So we summed over all the data points. And then we said, well, so we had different error measures depending on which function we used. So the linear regression had like least squares. The perceptron had the indicator function. So let's just use the perceptron. This was probably the simplest. This said 1 if the hypothesis and the label disagree. And remember, the label here was f of xi, right? So this basically says if h and the true thing it wants to approximate, if they disagree, then it's 1. If not, then it's 0. And then we had this 1 over n term to make this thing in 0, 1. Right? Great. So there's a problem with the in-sample error rate. One way of seeing this problem is, if I remembered this entire data set, I could get 0 in-sample error rate. I could just have the function h that just on x, then it looked in the data set and then it gave you the corresponding y. Then I would get 0 in-sample error rate. It's kind of cheating. Could also imagine that maybe the hypothesis I get depends too much on the dataset, and really, if I gave it a new point that was similar, it would do very bad. But that's actually what I want. I want to perform good on new points I never saw before. I don't really care about my dataset. This is just for training. I care about in the future when I get new points that are similar. So this notion is kind of captured in what we call the outer sample error rate. So this is also defined to be what the hypothesis says on x, and then what the difference of, actually let's just do it as the indicator function actually. So it'll be the indicator function, and then what h says on x, and then how this differs from what f says, right? The unknown target function says. So it's basically how much do our hypothesis deviate from f on x. So this is the same thing as before. But we want to rid the dependency on the dataset now. And to do this, we'll take the expectation with regards to x. So it'll be the expected x we'll consider now. So remember, in the unsupervised learning setting, we assume each of these data samples are independently and identically distributed. And it's this distribution of these x's we then take the expectation with regards to. Okay? So in this kind of way, this kind of captures, like, if we get new samples that are also from this distribution, what will our error be? So this is not something we can compute, but this is what we really care about. So this thing is something we can compute, and it's something we can design algorithms that actually try to minimize. This is what you saw in the linear models, right? We try to minimize this thing all every time. So this is something that's kind of like concrete. We can kind of measure, we can compute it, we can try to minimize it. Over here we have something that's a bit more abstract. We really can't compute this thing. But this is really what we care about. So we're kind of unfortunate here. What we really can do something about, we can't. So this is what we can do things with, but it's not really what we care about. We care about this thing. So the hope here is that the first thing approximates the second thing. Then if I minimize this, I'll probably also minimize the outer sample error rate. So then we say that my hypothesis, or the in-sample error rate, generalizes. I generalize from the data sample to the general case. So if these are close, we say that you generalize. So we can get guarantees on how close these two things are. We want them to be very close, right? Then they are approximate each other. And there's two different kinds of ways of looking at this we'll consider. We'll consider the VC dimensions. And we'll consider the bias variance decomposition. So in the VC dimensions, we'll try to make an upper bound for the outer sample error rate. And the upper bound of the outer sample error rate will be the in-sample error rate and then some penalty term. So if we had an example, then maybe the in-sample error rate would be, I don't know, 5% maybe. Let's just write this as 5%. And then the penalty could maybe be 2%. Then I would know that the outer error sample rate would be less than 7% with high probability. These are like probabilistic upper bounds or like guarantees. So if this was true, then I would know that I would actually have a bound on this thing I really care about by actually knowing only stuff about this, which is really cool that we can actually do these things. So this will be covered, how we do this will be covered in the VC dimensions. So you might now think, well, what is this term? What is this term? Well, this is a complexity term. It's a penalty term, actually. It's a penalty term that depends on the complexity of the hypothesis we're allowed to choose. So it depends on the complexity of our hypothesis set. So it'll be covered more in detail in the following videos, how we define this thing. So it'll be something we call the VC dimensions of H. So this is what this will depend on. So this is one way of finding the outer sample error rate. In the bias variance decomposition, we do something different. Here we try to decompose the outer sample error rate into two terms, a bias term and a variance term. So this is kind of different. Over here we try to have an upper bound, where we try to upper bound and get an idea of like how do we make sure that this guy doesn't get too large away from each other. And over here we can kind of decompose it into two other different terms. And it turns out that we actually have techniques of, if one of the guys is very, very bad and the other one is not, then we have techniques of fixing stuff. This is typically the case. Typically the bias is good and the variance is bad, or the bias is bad and the variance is good. So if, let's say that and we actually have techniques to improving both of them. And you'll see this much later videos. There'll be an entire sequence of videos targeting just this. But just for now, I'll just point out that we'll see a method called boosting that will fix bad bias, and if you had bad variance, we'll see a method called bagging that will fix this thing.